Chapter 5, Uniform Circular Motion. So here we're going to take a closer look at what it means to be moving in a circle. And to help introduce it, we have this comic caption says, "This isn't what she had in mind when Sylvia agreed to join Ed's study circle." Yes. Well, we will be studying circles, all right. And hopefully you also have your own study circle to work through these problems together at this point. All right, so first, what is uniform circular motion? Uniform circular motion is the motion of an object traveling at a constant speed on a circular path. So the constant speed is a key detail here. The speed isn't changing. Notice it is speed though. This is an instance where speed and velocity are different because it turns out the velocity will be changing in order for it to stay on this circular path and continue to move around and around. Now, what is the speed at which it's traveling? Can we relate that to other quantities in the circle? And it turns out we can. So if we think about our definition of speed, we know that speed is distance over time, right? So I could write that with an x and a t. So then we could say, okay, well, what is the net distance to travel once around the circle? To travel once around the circle is our circumference, which we could calculate with 2 pi r. So we have 2 pi r for the distance, and then for the time, we're going to fill in that that is our period, right? Which we've briefly seen in lab before. Period is, we use capital T, and that's to represent that the time it takes for the object to travel once around the circle. So we get that our speed is just 2 pi r, the circumference, 2 pi times the radius r, divided by the period t. So radius is from the center of the circle to the outer edge, it's half the diameter. And then the period, again, is going to be the time it takes to go once all the way around this circle. So that's our first introduction into uniform circular motion. Let's try out an example and see how it goes. All right, so example 1, a tire balancing machine. The wheel of a car has a radius of 0.29 meters and is being rotated at 830 revolutions per minute, RPM, on a tire balancing machine. Determine the speed at which the outer edge of the wheel is moving. Right, so we have this tire balancing machine. So it mentions the wheel of a car, right? And it also mentions the radius, gives us that that radius is 0.29 meters. So that's useful. There's this other piece of information that we don't necessarily understand right away. 830 revolutions per minute. What does that mean? Because that's not yet in terms of period, which should be in seconds. Instead, it's RPM, revolutions per minute. Well, this, it turns out, is going to correspond more to the concept of frequency, which frequency is 1 over the period. Because frequency is always going to have units of 1 over time, inverse time. And so to convert this to period, we just have to take 1 over it. And that will allow us to then have the time in the numerator as opposed to in the denominator. All right, so if our frequency is this 830 revolutions per minute, then our period t is just going to be 1 over that. 1 over the frequency, so 1 over this 830 revolutions per minute. And so we'll end up with 1 over 830, and I'm going to go ahead and flip the units and write them on the numerator, the top side, and that would be minutes per revolution. And so all we'd have to do there is then just convert it into seconds, and we are home free. We're ultimately solving for the speed, v, and so we can use the equation that we saw on the last slide in order to do that. So let's take a look at it all written out. I'll clear this so we have a clearer picture. So to get the period, once again, it's going to just be 1 over the frequency, 1 over that 830. So you get 1.2 times 10 to the minus third minutes per revolution, which we can then say, okay, the period is just that in minutes. The revolutions we can just kind of drop. That's all right. And then we need to convert to seconds. So to do that, we need to remember how many seconds are in a minute. There's 60. So we'll just multiply this here, canceling the minutes. So I'm going to put that in the denominator, put the seconds in the numerator, and we see that we have 60 seconds in 1 minute. So if we multiply this 1.2 times 10 to the minus 3 by 60, we get 0.72 seconds. And then we can plug into our equation for velocity, 2 pi r over t. We have 2 pi times the radius, 0.29 meters, divided by our period, 0.072 seconds. And it comes out to 25 meters per second. That's pretty fast. And we were able to solve it. It wasn't a particularly challenging or intense calculation in terms of math and algebra. The main challenge is dealing with figuring out, like, this RPM, how that relates to the period. Is that a frequency? Is that something else? So once we're able to relate that to the period, then the rest of it goes pretty smoothly. So this introduces uniform circular motion.